Why are some statistical mechanics concepts counterintuitive? Have you ever wondered why some ideas in statistical mechanics seem to go against what we naturally expect? It's a fascinating topic that challenges our everyday thinking. Let's break it down together. Statistical mechanics looks at the behavior of huge numbers of particles, using probability to describe how they act. This is different from what we usually see in our daily lives, where we can observe smaller, more predictable events. When we shift from certainty to probability, it can feel strange and hard to grasp. At the heart of statistical mechanics is the link between tiny particles and big properties like temperature, pressure, and entropy. Instead of tracking each particle, this field uses statistical methods to find the most likely states of a system. This means that while individual particles follow strict physical laws, the overall behavior of the system comes from averages and probabilities. This can seem abstract and surprising. One important idea is entropy, which tells us how many microscopic arrangements can lead to a certain macroscopic state. Entropy usually increases in spontaneous processes, showing that systems naturally move toward more likely, disordered states. This idea can be confusing because it goes against our usual views of order and chaos. Another reason these concepts can be puzzling is the difference between the time reversibility of the laws that govern tiny particles and the one-way increase of entropy we see in larger systems. While the basic rules for particles can go both ways in time, the overall system tends to settle into states with higher entropy. This creates a contradiction that requires us to think about probability and the behavior of many particles. Statistical mechanics also depends on assumptions like the principle of maximum entropy. This principle helps assign probabilities to states based on what we know, rather than on strict physical properties. This means that some outcomes reflected our understanding of the system instead of just the system itself. Quantum mechanics adds another layer of complexity. It introduces a fundamentally probabilistic nature at the microscopic level, changing how we think about statistical mechanics compared to classical mechanics. In everyday terms, statistical mechanics explains why gases spread out to fill their containers, why heat moves from hot to cold, and why some chemical reactions happen on their own. These common occurrences arise from the collective behavior of countless particles and their statistical tendencies, even if the underlying laws are deterministic or quantum mechanical. Overall, the counterintuitive nature of statistical mechanics comes from needing to think in terms of probabilities, large groups, and how behaviors emerge rather than direct cause and effect. Understanding this viewpoint helps clarify concepts like entropy, spontaneity, and the natural flow of thermodynamic processes, making the principles of thermodynamics more relatable and easier to grasp.